Hey, welcome everybody on the live stream and everybody who's here in the Zoom room as well. Will should be here any moment. We'll get started. Thanks for being here. My name is Alex. Oh, hold on. Yikes. Just mute myself on YouTube so I'm not hearing my own playback. My name is Alex McPhail. I am a Codesmith alum and I currently am the UX engineering director at a robotics company. And I'm here, I'll just be hanging out in the chat answering questions. Happy to chat about whatever's on your mind. And the real expert will be here very soon, so we'll just hang tight. If you weren't here before, or if you were here before, sorry for repeating myself, but go ahead and turn your cameras on if you feel comfortable, and if you like, you can put your name and where you're tuning in from in the chat. And like I said, Will should be here any moment. Welcome again to anybody who's just come in. Sorry for those of you who have to keep hearing me repeat myself, but we will get started here in just a few minutes. Will should be here any moment. My name is Alex. I'm a Codesmith alum and I work in the robotics space now. So I'm here to just hang out and answer questions or chat about anything that's on your mind. In either the YouTube chat for those of you who are live streaming or in the Zoom chat for anybody who's here. Not in real life,
Yay.
but you know. Hey,
Hello,
there's Will.
everybody. Good to see people. Thank you so much, Alex, for holding it down while I was delayed. Are we live? We are live. Look, there's me. While I was Look at that. Momentarily after. Okay. So, good to see everybody. We are going to dive right in and hopefully we will be able to cover. Yes, feel free to share in the chat where you are in the world. Looks like Alex already initiated that. Thank you so much, Alex. Welcome back. I think Alex has been, I don't know, maybe more or less on leave of sorts over the past uh, month in honor of a uh, new life. How about that? It's wonderful. And so let me just pull up my. I actually I did a version of this talk, which was a under the hood build out kind of hard part style of neural networks, and I did it on fab paternity leave. So I did it in person in New York on Friday, and I will do it multiple times over the weeks ahead. Uh, which I'll just show you I'll give you the slides if you want them here. Um, yeah, this is it. But we're not going to do that version today. So it was quite fun though. I'll just show you what we're going to have at some point if you look out for it, building out a full neural network from scratch, including gradient descent. Look at that, isn't that cool? and then multiple training iterations and some multi-layers or deep neural networks and backpropagation and all the core principles of it. But we're not doing that today because that's a 3-hour workshop, and we will do that at some point. So look out for that on your calendars. If you want to find out more, definitely go and I don't know, what can you do? Subscribe to me on LinkedIn. How about that? I don't know. That's a bit. Or join. Hey, go join the CSX Slack channel. I don't know. Maybe do people join? Do people use CSX? I think they do. Do people use Slack channels? Let me just share this with you. Have a look at the channel there, but also feel free to follow me on LinkedIn, and I will share when I'm doing a full run at that. In this workshop, we'll go a bit higher level and cover, and for those of you who've been to this workshop before, well, I kind of say sorry because you've seen something similar. But for those of you who haven't, fabulous. It'll be yes, Ginger. I go by Ginger Will. You go by Ginger Williams. There you go. I go by Ginger William. Uh, but Ginger Williams here says, is there a place to access the recording afterwards? Yeah, I think on YouTube. So you should be able to. And then, as I say, there will be a full deeper dive of neural networks out from scratch. Woo! In an upcoming workshop as well. But here, I think we will spend some time going through the key ML principles, machine learning principles from a slightly higher level, and answer all and any questions that you have about deep learning and neural networks in the chat. Feel free to throw those in. It'll be lovely to have those to guide our conversation. But without further ado, let's dive in to cover some of these topics. So as we dive in, I will spend a maximum of 5 minutes on our overview of Codesmith, given that they are our sponsor and the coding school behind this workshop. Let me just make sure my windows are not showing my you know how sometimes you have your windows open and they're showing your passwords, but I will make sure that's not the case. So here we go. Here we go. So as I say, here's the workshop that really dives into neural networks, and I will be excited to share this deeper dive version with all of you, and certainly happy to share the slides if you want to give me a message. What is it they do on LinkedIn when they try and bait people to engage with their content? Write link in the chat. No, right. What do they do on LinkedIn? They write like write downloadable in the comments, and I'll send it to you. And it's like all these very sincere people say, share with me, or building up the engagement that LinkedIn post needs. I'm not sure what I think about social media. Anyway, we won't do that. I'll share you a version of these slides with those who RSVP'd on this event. But as I say, we will now dive into. Please do not write downloadable. All right, here we go. So few words on Codesmith. As I say, the organization sponsoring this, it is probably best understood from the page here. We cultivate technologists. It's a coding school. It's a coding boot camp that thinks quite significantly differently from the conventional. Those are at the intersection of leading in society with hopefully the right values and the right desire to contribute positively and technology to meet this moment. It is nevertheless a boot camp that, not a term I love because it doesn't always express this, where graduates typically become a mid-level or autonomous software engineer across the full stack. And I think what we'll see today, as we try and build out some mental models of neural networks, is that full stack is expanding to include what I would call productized prediction, the ability to integrate into applications prediction, and that prediction might be prediction of user behavior, what in items might a user purchase based on what they've seen previously. Is the user likely to be making a fraudulent refund claim, or are they likely to be making a legitimate refund claim, meaning you can integrate into the product an automatic decision on whether to give a refund. That is, you can integrate prediction, a solid prediction as to whether the person who is requesting their refund in Uber Eats, in DoorDash, is legit in their request based on prior data, or whether their request is likely a fraudulent, opportunistic chance to get a free dinner. You are building a product around that prediction. That is a new part of the full stack engineer. And that's what the program at Codesmith endeavors to create. And part of doing so is building some pretty revolutionary things, like contributing to TensorFlow, probably now the second most popular as opposed to the primary interface for neural networks. This was TensorFlow JS, which is TensorFlow's effort to allow in the browser neural network execution, or at least interface. And some of the pre-processing layers of that were built by Codesmith students. But a range of different projects that are then celebrated in the broader developer community. Not a typical thing you'd see, of course, out of a coding bootcamp, but it's a bit different. And then a wonderful, talented community of people. Note the number one major for people coming into Codesmith is actually computer science, which gives you a sense of maybe the different approach that Codesmith takes to operating a bootcamp from your conventional coding bootcamp, and some recent offers from graduates that are speaking to what we're seeing today, this intersection increasingly between AI and software engineering. Here's a cognitive software engineer. That is a sort of another name for the kind of work we're doing here today together. I think there's an ML engineer here at TikTok, machine learning engineer at TikTok. That's not what we're necessarily trying to become in today's workshop, but at least be able to think about some of these topics. Okay, so I think that should probably be enough on Codesmith. The way it's achieved, by the way, is a timeless pedagogy, a teaching approach that is not new. In fact, it's very much what you hope you would find at a top college, one which is really focused on giving you the capacity to problem solve, to communicate difficult technical ideas for the rest of your career. They become the engine of your growth in new technologies, whether that is a UI framework, or whether that is a new, I don't know, neural network interface. And you see that in the graduates typically taking roles then in languages they're not even taught. With technically, we teach TypeScript and JavaScript just because they're a very broadly popular language with some interesting contemporary features, particularly asynchronicity. These are key features of modern programming languages that are in TypeScript and JavaScript. But over half of graduates aren't even working in that area. Nevertheless, the technology you teach does matter, so learn the most contemporary. This is the co-founder of Codesmith, who has done a lot of work in the ML space and has been very involved up until the beginning of this year in supporting our curriculum. And then we have a wonderful community of people. Note this diversity of schools. One of the kind of best things is people who went to really, a lot of graduates come from UCLA, UCSD, these kind of schools, but also along people who took a different path. And that all coming together is the magic of Codesmith. So if you're trying to get into the program, good luck. In the meantime, there's me, and we will, I guess, in a second dive in. But before we do so, we'll hear a word from Alex, who I think can also answer your questions in the chat, whether about Codesmith, about your career, and or even about the topics we're covering here. But here's what we're going to cover in today's workshop. we are going to focus on the macro trends of what's going on in the software engineering field that is leading to the value for all of you understanding, or at least having a bit of a mental model of deep learning. What does that look like in the edges and skills and capacities you need as a software engineer, as the stack, just for those who are newer to this, the stack being the core set of technologies you're working with. What is the expansion of those core set to be something a little bit more than what you've seen before? And then we'll talk about that expansion of knowledge requires, some effort. What are some of the core things that you should be looking into? And let's start building out those mental models today. And then what does a team look like once you are able to contribute in this broader sense? What does building products with prediction integrated look like? So before we dive into all of that, I will just pause for a second and pass to Alex, and I will shut up for a second and mute. And Alex, if you want to say hello for 30 seconds and then we can dive in.
Sure. Hey, everybody. Sorry to again to everyone who has to hear me repeat my introduction. But my name is Alex. I attended Codesmith in 2022. In June of 2022, I was an organic flower farmer. I graduated from Codesmith that fall, and now I am the engineering director at a robotics company. We are building autonomous drones to do sub-canopy surveys in forests for forest fire prevention and planned burning. So it's been an exciting and wild ride. It's a crazy time to be in this industry. And I will just be hanging out here to answer questions in the chat, or I'll post some like my LinkedIn profile and stuff like that if anybody wants to connect. Happy to answer any questions you have about Codesmith or any questions I can answer about the industry at large and things like that. So thanks for being here, and let's get into it.
Fabulous. And I just realized I need to spotlight, because otherwise, obviously, I'm really grateful for the folk of their cameras on, but when we're YouTube streaming and I don't have a person spotlighted, only the people who have their cameras on, I do believe, might show up on the YouTube stream. So I must always remember to spotlight whoever is talking, which is what I did there, as you saw, so that our people who are on camera, which is very lovely and very meaningful to me, are not scattered across the YouTube stream. So here we go. Let's dive in. We can be confident now from the stream that it's only me showing. So we have a set of new tools available to us, people. The shift to what I will call stochastic software. Historically, software is a step-by-step, if this, then that, not a probabilistic or stochastic possibility-driven mode of operating. You can't traditionally in software deal with nuance or interpretation of subtle human language changes, and the use of human language doesn't respond very well to being classed or categorized in a entirely deterministic manner. The rise of prediction, and specifically neural networks and large language models that can capture nuance, is a shift in the scale and domain of problems that can be solved with software. It moves out of software being unable to deal with giving legal advice or nuanced interpretation of imagery or generation of even artistic output, or not artistic, but creative output, into that being possible. It's actually not the only trend that's going on right now that makes software ever more central to our lives. Some of the other trends that are going on are one, the software definition of many things that were previously hardware questions. So, for example, the 5G rollout or robotics that were previously predominantly hardware questions have become increasingly questions where the hardest problem solving is being done in software. The fact that 10 to 12 hours of our average day is spent online, meaning the raw material of software, which is digital stuff, interaction on a screen like this, increasingly is our default mode of operating and is all there. It's not like 15 years ago where we had to transition stuff online. It's the default place in which our work takes place. But these three mega trends, one, the rise of the possibility through neural networks and large language models of stochastic and or what you would call nuanced software, AI, the rise of software as a place in which previously hardware questions like a 5G telecoms rollout or robotics are taking place not in the physical infrastructure, but in the software layer. The 5G rollout was primarily a software rollout as opposed to a pure hardware rollout. These are the, shifts. And then, sorry, the third one, the default digitization, the default digital state of most of life. These are the mega trends that mean software is taking its next stage as its centrality to our lives. And software engineers are the builders of that. So, we're going to dive into that. As I say, that should then give us the foundations to identify what are the pieces that, as a software engineer, which I know many of you in the room are, you can be investing in to be able to compete in that era. A bit of context, I think, behind those mega trends. I'll try and keep this fairly short. There's another talk that I give on the tech market that you're welcome to attend. But the last couple of years have seen widespread layoffs and, more importantly, hiring freezes, which we're really coming out of now. And obviously, part of that's been tied to interest rates, which are clearly over the next 3-4 months going to drop, and that will change the relationship between between investment and I guess software spend. But it has been a period of 2 or 3 years with really significant shift in the dynamics of the industry. Some optimism for it. Most people did find roles soon after being laid off, as specialist software engineers. The majority were not software engineers. And then here's a major one. One of the aspects that the fall off of tech hiring led to was an opportunity for firms that were not maybe established as tech firms to establish themselves as tech-oriented firms. So within finance and healthcare and energy, a huge growth in investment in technology, at least for Codesmith grads, a significant increase in hiring in those domains as opposed to in traditional tech. And the opportunity for them to do so with leadership that really understands how to build a great tech team. Because no longer were they doing so kind of outsourced, but often they brought in that director of technology from Meta, formerly Facebook, and made them the director or VP at JP Morgan and said, hey, how do you make sure that a software engineering team is run in a way that gives the company an edge, that the product they're building has a commercial edge by the quality of its software? How do we do that? And that was a major shift, was a full investment, so that you're no longer, if you join a JP Morgan or a Walmart instead of a Amazon, you're no longer compromising on your engineering experience. It's now much more of a case of this is a professional opportunity for you and also a chance to make an impact maybe in a field that matters to you. But these are the kind of mega trends going on behind the scenes. And as I say, they're tied to some shifts in the kind of tools available. And so it's kind of a strange coincidence that if you're a healthcare firm now or a finance firm now, and you're trying to make software a central part of what you're doing, or you're a law firm now, or you're a professional services firm now, you're trying to make software a central part of what you're doing, the tools available for you are becoming more suited to your problems. And those tools available particularly are new, let's call them AI tools. the kind of problems you're dealing with as a law firm or as a finance firm are problems where if you can increase the output of your software engineering teams, if you have available to you new approaches that deal with nuance as a sort of suite of software tools, then you're better able to solve your organization's problems. If you are a law firm, you could not previously ever think about software being part of providing legal advice. It just wasn't going to work. Now it's possible. If you're a healthcare firm dealing with, or healthcare organization dealing with the extraordinary complexity of trying to integrate 20 different trading off vendors within your healthcare system and trying to make it more of a established software layer to improve provision to patients, if you have your software engineers better able to work at a higher multiple of output, you're able to start to tackle some of the problems that previously were intractable in healthcare. So these are the funny, on the one hand, this shift in demand, particularly to healthcare firms, areas that were previously not tackling their problems with software, and at the same time, a potential rise of available tools to help handle that new domain as well. So these are the things going on behind the scenes. It leads to, so yeah, that's the things going behind the scenes, right? Macro trends in tech and the rise of new tech and new tools, particularly broader than just AI and machine learning. Also, as I say, software being applied increasingly to data that is default digital, not having to be transitioned into it, and also the rise of software defined hardware robotics work. But the biggest one of all is the rise of AI and ML tools. Now, what does it mean for you as, let's say, many of you in the room are software engineers? What's it mean for you? Well, there are 5 things, and we didn't dwell on them, but they are the things which we look for in Codesmith candidates to join the program, that make a great software engineer. And some of them interplay with each other. Some of them you can't really have without the other. But the 5 things are capacities, problem solving, and technical communication. That's the ability to break down a demanding, complex set of needs, maybe from a stakeholder, maybe from a collection of different stakeholders within an organization, and help understand what's possible in tech, in technology, what they can possibly be implemented in the software layer as a kind of converter, like you're a conduit, you're like a converter between the need of the organization and implementation in software. That's engineering problem solving. Technical communication, the ability to help others understand what you're doing. That only becomes more important, people, when you're dealing with software being at the center of problems that previously were not solved with software. So when we have graduates at Codesmith who go and join a company as a software engineer, lawyer, or software engineer, designer, that fusion role where you are now putting software in to areas that previously were not dealing with that, you better be really damn adept at figuring out the need and what's possible. And you better be really damn adept at explaining to people around you, non-technical and technical, what you're doing. But that doesn't change. It's just more of it. That's what was always making a great software engineer. What I think does have some, and non-technical communication, which is the ability to, do so in a hopefully relatively empathetic way, also doesn't change. Maybe put that one above here. Also doesn't change, right? What does have some evolution is, oh, by the way, I've been in meetings for 8 or 9 hours, so forgive me if I seem in any way harangued. I'm sorry. But what does evolve are these 2 areas, and that's what we're going to dwell on the rest of this workshop together, which is your engineering approach and the principles. This is not the tools you use. This is in engineering, thinking about how to what is the concept of state management? Not a given state management tool, but what are you doing when you're trying to persist state over time and enable others in your team, state being the fancy word for the data as stored in the computer that describes how the application is right now. And what are you doing to manage tracking how it's changing as the user takes actions or a server provides updates? What is a system architecture, or not even that, what's the design principles that can help you do that well? That's your engineering approach or principles. It includes mental models, and I think there's some new ones thinking about the nature, by the way, I'm afraid I wouldn't even say LLMs here, I'd adjust this and say of prediction and statistics. When you're building a neural network, you are at your core, when you take a training sample, when you're using training data, you are taking a sample of all possible, the whole population of possible interactions or outcomes. That is a question of probability and statistics. How are your mental models around those ideas? And that's a workshop that I'll do in the next few days, even maybe by the end of the week, on some of those concepts. And then your domain knowledge. This is the fifth area we think matters. So problem solving, technical communication, non-technical communication, your engineering approach and principles, and finally, excuse me, the knowledge of the given domain. As a software engineer who wants to work right up against and with machine learning engineers, and you're not going to be a machine learning engineer, that's an additional set of knowledge, but right up against, there's an area of knowledge that can make you that effective software engineer who can work effectively adjacently with the machine learning engineers. And particularly, that is how to think about model or data pipeline. That's the flow of data that contributes to making a good prediction. And again, that prediction might be whether the user refund request DoorDash is fraudulent or not. But that prediction might also be, people, what is the best phrase or series of words to answer the prompt, its own series of words? What is the best set of words that most effectively answers that, at least, according to some model benchmark or some feedback from users? That flow of data that's going to ensure the prediction is good, and then as that data, as the user interacts with the prediction, maybe complains that your claim that their refund request was fraudulent and says, excuse me, I'm going to show you why that's not the case. That's new data. Your model pipeline or your data pipeline is that idea of making the prediction initially as effective as possible, as good as possible, and then refining the prediction, refining the model based on new data. Could be the user's interaction with the old prediction. That's the model pipeline. Deploying, putting it online, that predictor, that model that can look at a new situation and automatically determine fraud or not, or look at a new prompt by a user and automatically determine here's the best phrase response, i.e., answer to the question. Infrastructure, the build out around that deployed model, that prediction that is live, but also user experience as a designing good user experience around AI tooling. There's a big difference between the rollout of AI tools that are bolt-ons to software versus, I think it's fair to say, immediately good old Apple. They must just have really visionary product designers, because their effort at AI, Apple Intelligence, instantly shows great instincts about how do you build these sorts of tools in to make an exceptional user experience. Those are things that, as a software engineer, if you can have good models around, good mental models, good mental models around, you will have an edge as a software engineer. Okay, so with that in mind, let's talk. Let's talk It's the title of this talk, by the way. I apologize. I would be questioning the title of this talk. This is on me. There will be a deep learning and neural networks full deep dive in the next few days. Like I say, I gave it on Friday in person in New York. Shout out to the lovely audience who joined for that. I think Jesse, who's always come to workshops there in New York, Sky, Miri, Nimi, a whole bunch of great people who came on Friday. But this is probably going to be not the deeper dive on deep learning, because that was a 2 or 3 hour workshop. So I apologize that the title of this talk is maybe a little bit of a misnomer. Um, well, hey, there we go. We're getting a bit of a framework. But let's talk prediction, dive into neural networks, and see if we can hit some of these other pieces: LLMs, video, audio generation, and an engineering team in the AI era. Let's see if we can hit on these areas while we have time together. So, yeah, so it's all prediction. All prediction being, what is prediction? It's taking prior patterns that we've identified in our data, or prior data that we've given some sort of potentially labels to and categories to, and then using that as probabilistic, it may or may not be 100% accurate, generalizations for the rest of the possible scenarios, the rest of the possible population. So, for example, the likelihood of our DoorDash item not showing up and us making a refund request being fraudulent or not. We're going to use maybe 10,000, maybe 100,000 prior cases of users of DoorDash or Uber Eats or Grubhub, whatever, requesting a refund, and then a customer service rep directly messaging with them and determining whether or not to give the refund. We're going to use that sample to estimate, to make a prediction of the broader population, including future users making requests for a refund. But we're only going to need to look at maybe 10,000 to be able to make a decent prediction across all possible future scenarios. If we find that our sample is not reflective of the broader population, maybe over time users' behavior changes, then we'll need to update our sample. But at our core, we're making predictions of the broader, we're making generalizations to the broader population, including future scenarios based off a narrow sample. And that is it. When we use a large language model, we're making broader generalizations of how language can be used based off a smaller sample. Now, the smaller sample is all the text used on the internet so far, but it's still only a subset of possible ways in which human language can be used. But we're making, therefore, a generalization and able to, therefore, make a decent prediction, we hope, in a future scenario of, in the case of a large language model, what the next word would be, and therefore what your answer to a question would be. And in the case here of a refund request, what the likelihood or the probability, sorry, of the refund request being legit is versus being fraudulent. So what do we use for that? We use historic data patterns. So we may have 10,000 examples, 10,000 people who've made a refund request. The determination afterwards by the customer service rep of that was legitimate, fraud, true, fraud, true, most of them probably true, a few of them fraud. And then we have data on each of those cases on what were the potential salient factors that the customer service rep considered, and maybe they didn't consider, but we're going to see them now. And those are things like how many times that person previously said, hey, my item didn't show up. Maybe it's 5 times, maybe it's 10, maybe it's never. How much was this refund request for? Maybe it's $10, maybe it's $500. What did the delivery driver say? Yeah, I delivered it, but I don't know what they're talking about. Or maybe they didn't respond. These are factors that then allow us to generalize from this small sample to future scenarios and allow us to in future make a prediction If someone has, let's say, a large number of previous no-show claims, a very short purchase history, and I don't know, let's say, I don't know, multiple accounts on the same IP address, that was in this small sample, 10,000, 100,000 cases, associated, not predictive automatically, just associated, not causally related, just associated with it being a fraud refund request. Therefore, in this next situation, we can automate the block on refund. Or if we found that 99.9% of the time, when somebody made a refund request and had no prior refund requests, and they only had one account on that IP address, and the dollar transaction value was under $30, it turned out not to be a fraudulent claim and they got the refund, then we can generalize that. And in the next case, when someone makes a refund request and they've got no prior refund requests, they have one account on their IP address and the basket size was $15, we can automatically give the refund. And that is prediction in action. But the model training part of that is working out what is the best pattern, what are the most important factors by looking at all that prior data, what are the most important factors associated with what the customer service rep determined was fraud and what the customer service rep determined was not fraud, allowing us to automate that prediction in future. But note, people, this informed prediction is based off multiple places where humans are at play. One, the customer service rep determining do we give a refund or not is a human decision. They're bringing all their stuff to that. But another is also the sample we're using. It's going to require ongoing engagement and refinement by a data scientist to assess, is this sample we're using reflective of the population at large now? So, for example, let's say the sample had as I say, multiple cases where someone did 10 refund requests within a week and they had 5 accounts on the same IP address. Fraud, fraud, fraud every time. And then, God damn it, it turns out that actually that's pretty typical of people moving into a student dorm where the address is not fully known. Like, suddenly your sample doesn't include all the cases where multiple refund requests within a week, multiple accounts on the same IP address that are all brand new. That sounds a lot like somebody rocking up at a dorm, multiple people at a dorm with ambiguous signage and making multiple requests for refund because multiple times in those first few weeks, all those people all on the same IP address didn't get their items show up. The population is not being well sampled, or the set of possible outcomes was not well sampled in this model, and therefore is not reflective. But again, that's a human decision. So all these places where humans play a part that ensures the model is either not effective or carries with it biases that may be reflective of the person's values who made the choices, but now it's being automated, meaning you don't get a chance to go and check on it. So it better reflect the values that the organization wants to be reflecting. For example, maybe, I don't know, credit score was a major factor in determining whether somebody's refund request is legit or not. I don't know, credit score, whatever. Credit card history, I don't know. Does the company want that to be used as a factor? Once you're systematizing that in a prediction, you've got a lot to be held accountable for to ensure that that is something the company actually wants to automatically include in their decision of fraud or not. Okay, so this is prediction at its very core. It actually translates directly into prediction using neural networks. It is the same idea fundamentally of generalizing from a small sample to a larger population based on statistics, based on the ability to hopefully mirror from a sub part of the population the broader population. So let's look at that with neural networks. Let's just see if there's any comments in the chat, because I am. And yes, people, I know we're going to go over very slightly here, but we won't go over too long. And I'm grateful, people, for your engagement here. Okay, so neural networks basing the prediction loosely. It's a technique for being able to identify the patterns in our sample of data, that can be generalized to the broader population. So we could use a neural network, by the way, actually, to assess the different importances or influences of these factors, no-show claims, purchase history, whatever. You could certainly use a neural network to identify the best associations, matches in our sample of, let's say, 10,000 people who made refund requests, with whether or not it was fraud. We could certainly use a neural network to assess for our sample what are the best matches, what is the best associations, what are the best importances or influences to be given to different factors in determining for our sample whether or not the refunds were fraud or not. And then we can generalize from that. The neural network is our technique for figuring out the patterns in our historic data or in our sample data that we can then best generalize from for our entire population. So take a look at this example here, though. We're going to use it for image recognition or image classification. And people, some of the factors behind neural networks have been around since the 40s or 50s. One of the kind of core pieces of perceptron, which is a single layer neural network, has been around since the 1950s. What's really transformed in the last few years, really 10, 15 years, is the computational power, the interest, the research interest for sure, but also the computational power has made neural networks, their performance across a wide range of tasks dominates, outperforms many, many other approaches. So whereas there are a range of techniques that you could use for classifying images into, is this a 9 or an 8? Neural networks turn out to pretty consistently achieve the best approaches. They're the technique behind large language models. They are the technique, or transformers are a version of neural networks, a technique within that domain. So they've become, albeit only analogously related to the way the brain processes information, although some interesting research suggesting maybe closer to how the brain processes information. One of the biggest blocks people have in associating with brain approach, the approach to the brain, is a key part of neural network design is this technique called backpropagation, which, again, when we do the deep dive on this topic in a few days, we'll talk through. But backpropagation, the algorithm that ensures you can re-weight and find out incrementally the most optimal pattern of influences between, in this case, for example, the dark shade areas, and predicting whether it's a 9 or an 8. We'll talk about that in a second. Backpropagation being the key algorithm introduced by someone called Jeff Hinton, who I think won the Turing Prize. That doesn't mirror how the brain works, but there may even be suggestions that it does. So these don't directly match the brain, but have similarities and potentially actually turn out to have more in common with the brain than even previously thought. But to look at them for a second. Okay, predicting based on brain structure. So first thing is to recognize that if we're going to make decisions of nuanced human stuff, it has to be captured in data. So we may see a handwritten 9 here, and our eye can recognize as a 9. The process by which that happens is so profound that we couldn't even think through how we're doing it. What am I seeing that makes it a 9? Same with the 8 here. The computer needs to have a set of instructions to do so. So that means, firstly, even capturing the image of a 9 as something that is recognizable to a computer. Well, recognizable to a computer in this case means the light areas as ones, and the dark area, we've got kind of an inverse here. The dark area here is zeros. So let's say we kind of flip this. The dark areas as ones and the light areas as zeros. These are our pixels, capturing the shape, the dark area represented by ones. And in practice, this comes from a data set called the MNIST dataset, National Institute of Standards and Technology, that worked with the US Postal Service in the 80s to try and improve handwriting recognition, to improve postal sorting. So this has been worked on for a long time. The performance went way up in the last 10, 15 years as neural networks really kicked into gear. Particularly, as I said, the computational power behind them, that means the computers have grown far more, powerful. So, yeah, this in practice would be the MNIST data set wouldn't be a 5 by 5 grid of zeros and ones. It would be a 28 by 28 grid of many values of grayscale, from 0 to dark shade, gray, dark gray, capturing the nuance of the human handwriting. So the goal is to write an algorithm that can recognize 9s or 8s so that they can classify, mail for zip codes, zip code classification, for example. We could write individual instructions. We could even try to categorize, or not categorize, list out all possible shapes of 9s, all possible shapes of handwritten 8s, all possible shapes of handwritten 9s that could ever be with different shades, and try and write rules and deterministic instructions for that. Even within a 28 by 28, 724 pixels, with maybe shades of 0 through 1, with, I don't know, 0.1, 0.2, 0.3, all the way through to 1, or maybe 0.01, like 100 shades of gray. The number of possible ways of doing a 9 and an 8, even if you were to kind of orient them to be within a expected area, which is all pre-processing, making sure data is kind of consistent in its structure before you try and run an algorithm on it. If you were to try and list out all the possible 9s you could possibly have, you're talking a number you can't even calculate, an unfathomably large number. So instead, we have to take a subset of 9s, a subset of 8s, and then, just like before, try to generalize to all possible handwritten 9s that could show up. The way we do that in this case is to give importances, influences, or weights to each of the given pixels. If it's going to be a 9 in this set, in our sample, and this is, as I say, what we'll go into more detail in an upcoming workshop, in our sample of, let's say, 100 handwritten 9s, which typically are the pixels that are most associated with that image being a 9? Which pixels are typically dark when that image is a 9? Which pixels are typically dark when that image is an 8? And that would be a single layer neural network. We give a set grid, almost directly corresponding, at least in the simplest form, to the grid of values representing the 9. We give a grid on top of it of weights, importances to each pixel for whether it's a 9 or whether it's an 8. And that's it. Now, in practice, neural networks become powerful when you add multiple layers. So not directly this pixel's influence on it being a 9, this pixel's influence on it being a 9, this pixel's influence. By the way, in this example here, you can probably tell that these 3 pixels here are the influential ones for whether it's an 8. If they're zeros, it's a 9. If they're ones, it's an 8. Where neural networks start to get really powerful is when you add another layer. So you have an importance that you attribute to each pixel for it being a 9, but not directly. Instead, you have an importance you attribute to each pixel for some intermediate value that then you attribute weight or importance to that intermediate value to determine whether it's a 9. This is multiple hidden layers. These are the layers in between, so you don't directly say this pixel, this pixel, this pixel each have individually this influence on whether it's a 9 or an 8. Instead, you say this pixel has influence on this potentially sub-collection of pixels that they themselves have a level of influence on whether it's a 9. But there's another sub-collection of pixels that have a different influence on whether it's a 9. What you're doing there is you're starting to capture sub-shapes, or what they call edges, within this grid of numbers, where the neural network can kind of see light, shade, light, and starts to see those patterns. The training stage is taking 100, 1,000 or more of these handwritten 9s, handwritten 8s, and trying to work out, even with multiple layers of influences, of weights, what is the best possible combination of those that matches this image with whether it's a 9, this image with the fact that it's an 8. And that's our training stage. But remember, we're still using a tiny sample of possible handwritten 9s, of possible handwritten 8s, and then going to generalize from that. But that, of course, requires it to be a representative sample. And so we're going to do all sorts of validation steps to confirm, did we end up with the best possible combination of influences or weights that we attribute to the pixels directly, or to intermediate steps before we determine it's a 9 or an 8. And based on that, can we generalize it to the broader handwritten numbers population? And if we discover that for our sample, what would we do is working or not, we would probably split our sample into the ones we use to develop our influences, weights, importance that we attribute to each pixel, whether it's a 9 or an 8, and then test it on another portion of that same sample. And based on that performance, the performance in that further part of the sample, be confident we can then use it on the broader population and start to recognize handwritten digits beyond the source sample. And that's the running of the model ongoing. So with the training of the model, we might then validate it against more samples, and then we start to use it for actual making predictions beyond the sample into the population at large. But if we're finding it's then not consistent, maybe human feedback is indicating it's making bad predictions, maybe our sample was not reflective of the broader population. And that's where we'd start to update the model with new data. Okay, I think for today, and this is used far beyond just pixel or collections of pixel classification. And as I say, we'll dive much more into this in this workshop here, where we will actually go about building out those grids of influences we attribute to each pixel. And even building out, as I said earlier, multiple layers of grids of influences. And then join that up with some of the creative approaches like convolving a kernel of grid of influences across an image, as opposed to taking all the pixels and seeing how they all influence, but focusing steadily on different sub pieces of the image. Some of the other challenges that come in neural networks, like the vanishing gradient problem. But that's another workshop. Hopefully this gives us a starting point to bounce from. I know we're already going over. I guess a quick thing I'll just share in addition here, and look out for another workshop where we go into large language models as well, but that's a separate one. Just to share the prediction tool that we can build, like a neural network, has to be integrated into a product. Otherwise, it's just a piece of research. In fact, actually, to work out the best for our sample, and it's already sounding quite researchy, right? There's a reason they call it data scientist. working out the best combination of influences of each pixel for our sample and how well it mirrors the population as a whole all sounds very scientific, right? Like sample, population, working that out, that's a data scientist. That could be happening, people like that's a kind of tweaking and playing and experimental. Is it working? What's working well? That don't sound like software engineering. Software engineering has, is it working? We're dealing here with incremental trade-offs and creativity, and that's the nature of the data scientist role, is to work out what are the best approaches to get our sample to capture the patterns in our sample and generalize it to the population. The patterns might be the association of pixels with the number 9, the association of pixels with number 8, or it might be the association of certain behavioral traits of a DoorDash user with whether it's fraud or not. When I say behavioral traits, I mean choices they've made previously to request a refund or whatever. That's a data scientist. They have to understand the math and statistics and probability behind building those generalizable models or predictions. Then there's the ML engineer. They have to ensure that, great, thank you, data scientist, it's working for the sample, but damn, we got to get this prediction online. We got to make sure that if we're going to be making changes to it as we discover whether or not it represents the population as a whole, are we going to be rerunning it? Are we going to be retraining it? Are we going to take the sample all over again and test all the possible different combinations of importances and influences we give to different pixels, for example, or in a large language model, different ways words are combined up? Are we going to do it all over again? The ML engineer goes, oof, that's going to cost us a lot of money because we're going to be testing out little changes, tweaks, and this is a separate talk, but tweaks in the importances we give to, let's say, each word combination in a large language model or each pixel combination in an image in our vast sample of images or our even more vast sample of human language use. Are we going to be retraining, in other words, re-establishing what the best combination of influences and importance we give to those pixels, to those words, whenever it proves not to be quite right? Or are we going to be able to maintain our existing model and tweak it or fine tune it? That's where our ML engineer comes in. Make sure that prediction that you're going to build into an app is fast because the training takes time and even the deployment of the model and then using of it may or may not be as quick as the user needs. Is it cheap? Is it up to date with the user's not feedback in terms of writing, but feedback perhaps in terms of action? They contested the automatic lack of refund on DoorDash, or they did the thumbs down on ChatGPT saying, no, that answer wasn't good. Is it going to be up to date and is it going to be live on the internet? That's the ML engineer. They have to understand the math behind the prediction and they got to understand computers, how to make sure it's there's a lot of understanding of how you split the tasks up, for example, across multiple machines. That's both a mathematical question. Can you split up the task? If you're doing, I don't know, it's too in the weeds, but if you are if you are training the neural network and thinking about how convolving the given feature is working, are you it is both a mathematical question, understanding, I don't know, how matrix algebra works, how matrix linear algebra works, but it's also a computational question of how do we distribute tasks in parallel, um, such that they complete more work at the same more work more work in the same amount of time. It's both a mathematical and a computational question. And that's what makes an ML engineer role such a fascinating and demanding role. You've both got to understand the math, the possible, or the kind of analytic constraint, and the computer. the computational constraint and possibility. Very, very interesting. Then you've got your software engineers. You've got, for sure, building the rest of the app. Let's come back to that. But you've got the software engineers who are helping the ML engineer, and sometimes there's no ML engineer and it's just a data scientist who have never deployed a model, or it's an ML engineer who's helping the data scientist but doesn't have the time to deploy the model, or it's helping the ML engineer who definitely knows how to deploy the model but would love to have their software engineer be thinking ahead, and or that their partner software engineer be thinking ahead about how to ensure the data that is being passed to the model for the prediction. Let's give an example. Suppose in this case here you've got lex.page that is a Google Docs, a text editor where you write stuff and then you ask for it to be proofread. You press proofread it and it comes back with grammatical corrections or whatever. That's being passed to a model that has previously seen patterns of scrappy text and nice text, and is able to therefore make a good prediction of what your scrappy text should be looking like after it's been proofread. Good text. The machine learning engineer may be super experienced and integrated in the team, but maybe they're grateful when the software engineer says, let me make sure that the text that I'm sending to you from the user typing to be proofread is pre-processed in a format that is model ready. To do so requires you to understand the underlying principles of what a model's doing. What is a pre-processing stage doing to ensure, as we talk about in the deep dive on deep learning, as we did on Friday, what's the model doing, or what's the pre-processing stage doing to ensure that the model sample, which has been generalized and therefore is making the prediction, is representative of the population, where the population is the data you're sending. Is one example of the data, is one example of the population. So you understanding that is a real edge as a software engineer, helping integrate the prediction into the app, thinking about pre-processing stages, data pipeline, thinking about deploying models in, it's no different to using Docker and Kubernetes for other deployed servers. Thinking about API design, both from the ML engineer's perspective, but also from the software engineering team's perspective. You as a software engineer who can work adjacent to the ML engineers have a real edge. And then there's the rise of alternative tools, or a range of tools to help you improve your productivity as a software engineer. I think having an edge to know the constraints of those tools and how to, think about large language models is very valuable. And I'd recommend you go to the LLM workshops with James Laff at Codesmith. But that's the other place all this sits in. So there we go, people. Thank you so much for sticking with me on that one. I'm looking forward to doing, as I say, a deep dive on these to come, but we have more content on this. But that's it for now. Let's. What I was going to say is, yes, none of this stuff is beyond you all. I do think you want to get the mental models down of some things that are not. We talk about at Codesmith, understand software engineering principles really well, and any tool, framework, whatever becomes, you figure it out. There are some mental models here that are different, particularly statistics and prediction, that do not sit as, oh, that's just more engineering. No, they're slightly different. It's, oh, that's more analytic research or science. So if you come, as many people go to Codesmith do, come from, I don't know, mechanical engineering or, I don't know, biostatistics or bioinformatics or whatever, they may sometimes be better prepared, better positioned for, this sort of readiness to work with ML engineers because they've thought a lot about sampling, generalizing, probability, prediction as part of their work in other fields. But that's some of the mental models you want to establish while recognizing you fundamentally still have a crucial edge as software engineers because just the domain that software can be used for now has grown substantially into areas that include sophisticated prediction. But you want to be part of engaging that prediction in product. And that's where you as software engineers come in. Okay, Prana says, It was a great talk. Oh, very nice, Piranha. As a beginner in the field of ML, I have a question as below: how to choose an ML model for a given problem. As I say, it's an experimental thing. Go to the deep learning follow-up I'll do on this, where we dive into this more fully, and I think you'll start to see you'll have a full framework. Let me just show you. I diagrammed it. It's very diagram heavy. Let me just show. Oh shoot, my laptop's running out of batteries, but it's plugged in. That's not good, is it? Something's up. Let me just show you this because that's why my computer's struggling. But if you take a look at this here, Piranha, this was the whiteboarding. So you can see the beginning kind of there of a framework, and you can see the sampling bit there. So when you're choosing your model, you're determining things like how well does it apply to the sample, how well does the sample reflect the population, how well are you maintaining the population being consistent with your pre-processing. These are all the kinds of things that go into model selection. And it's not purely, an art, although it is somewhere between an art and a science. It is also testing benchmarks, performance. It is looking at research papers and seeing what is working best for a given data type. Well, not data type, sorry, no, data type, a given kind of category of problem. And that's why it is a very, you know, and that's what's so exciting is that so much of the contemporary work that's being done is to say, well, actually, for this type of data, when it's been handled this way, this model worked extremely well. And the latest research papers are all that kind of live refinement to improve model performance. Does it match within the sample data? Does it identify the patterns as well as possible? And then also model performance and efficiency. Did getting to finding those patterns in the sample data take a lot of money and a lot of time, or a bit less money and a bit less time? That's what all that research that comes out, cranked out of both the Googles, the Amazons, but also the research universities, is all trying to do. Identify the best model for the given problem and the cheapest and most effective model for the given problem. So great, great question, Piranha. That's a core part of the job. Okay, people, let's leave it at that. Thank you everybody for joining. Thanks so much. To Alex earlier, sorry my laptop's got choppy. Thanks to our friends on YouTube and on LinkedIn. It was great to have you all. More to come. Look forward to seeing you all soon. Thank you, Bob. Cheers, Dalen. Thanks, Fish. Thank you, Jim. Lovely to see you. Thank you, Sanai.